Continuing on with the ratio test, we want to determine whether the following series converge. So you can see here that this whole piece is a sub n. And I notice a lot of powers in there. Factorial is like a red flag that you need to do the ratio test, but exponential functions like this also are a really good candidate for the ratio test. So we want to take the limit, r is equal to the limit, as n goes to infinity of, all right, so it'll be negative 10 to the n plus 1, because we're going to do n plus 1 divided by a sub n plus 1 divided by a sub n. So negative 10 to the n plus 1 times 4. Now this is where you really got to watch out. That little n in there turns into an n plus 1. So it becomes 2 times n plus 1 plus 1. And we're going to make a little note to ourselves to watch out. Right? That's where you're going to make a mistake in the ratio test, is if you do that wrong. That simple substitution, that's a long time ago you learned how to do, and it all seemed so easy in algebra class. And now, if you forget it, then all hell breaks loose. All right, then we're going to divide it by a sub n, which is, of course, negative 10 to the n over 4 to the 2n plus 1 times n plus 1. All right, so then that would be equal to the limit as n goes to infinity, negative 10 to the n plus 1 over, and then this would be 4 to the 2n plus 2 plus 1. So that'd be 2n plus 3 and n plus 2. And we're going to multiply that by, and then reverse this, 4 to the 2n plus 1, and then an n plus 1, and then a negative 10 to the n. All right, now I'm not going to bother to rearrange all the time. I rearranged for the first couple because you were just learning, but now we're getting better at it. So we'll notice that the two negative 10s here, they go together. So there's one more up here than there is down here. So I'm going to end up with a negative 10 up here in the numerator. Similarly, if I look at my 4 to the 2n plus 1 and a 4 to the 2n plus 3, there's 2 more down here. So that'll be 4 to the 2 left over. If you'd like, I can show real quick. 4 to the 2n plus 1 divided by 4 to the 2n plus 3 is 4 to the 2n plus 1 minus 2n plus 3. It's 4 to the 2n plus 1 minus 2n minus 3, which is, in fact, 4 to the negative 2, which is 1 over 4 squared. Just a little review of basic pre-algebra. Okay, so that's informing how that part works. That's why that's 4 squared. And then I'm left with an n plus 1 and an n plus 2. So be it. I'll just leave it with an n plus 1 and n plus 2. So I guess I'll write it right here. So this is the limit as n goes to infinity of, okay, so I have a negative 10 in the numerator. I have a 4 squared, which is 16 in the denominator. And then I have an n plus 1 in parentheses and an n plus 2 in parentheses. Because, of course, it's not 10 times n. It's 10 times the whole thing. That would be equal to, now 10 and 16 can get pulled out because it's the absolute value of them, so it's going to turn the 10 positive. So I can actually write 10 over 16 here. We learned a long time ago that you can pull a constant out of a limit like this. So I pull the constant out. Yes, I know I can reduce that. I'll do that in the next step. I just didn't want to do too many things at once. N plus 1 over n plus 2. Well, yet again, that's infinity over infinity, so I'm going to be doing a L'Hopital's rule. And I'm going to reduce the 10/16 into 5/8, because 2 goes into both of those. And then the limit of this is the limit as n goes to infinity of the derivatives, which would be n plus 1's derivative is 1 over 1. technically absolute value, but whatever. It doesn't make any difference because everything's positive. So that would be 5/8 times 1, which is 5/8. So there's R. R is 5/8, and 5/8 is less than 1. And remember, when it's less than 1, this series will converge absolutely, and therefore it converges. So I can just say that my series, -10 to the n over 4 to the 2n plus 1 times n plus 1 converges. If you want, you can say converges absolutely, but converges absolutely is just a type of converging. Remember the theorem. If it converges absolutely, then it converges. So we can just say converges. Next one. So I have n equals 1 to infinity, -1 to the n over n squared plus 1. Okay, so let's think. That's b sub n right here. I'll do it in orange. So, or a sub n. I mean, it doesn't really make any difference. I'm just choosing letter b because I'm in problem b. And so that would be r would be equal to the limit as n goes to infinity of, and then I want to take n plus 1. So I'm going to take -1 to the n plus 1 over, and then it's n plus 1 quantity squared. The whole thing has to get squared. Plus 1. I'm going to divide that by, so my division symbol got weird there, divide that by -1 to the n over n squared plus 1. Okay, so let's just real quickly write that. That's the limit as n goes to infinity, and we all know that we're going to be flipping the sucker around. And it's going to be -1 to the n plus 1 over your choice. You don't have to FOIL this if you don't want to. I don't want to make you feel like you have to FOIL these all the time. Like if it was cubed or to the 4th power, you wouldn't want to do that. So I'll just leave it like this, because that's more likely the way you're going to want to leave it. And then I'm going to put n squared plus 1 over -1 to the n. But if you're sitting there thinking, oh, I could distribute that easily, sure you could. But if it was more complicated, like a 4th power, you wouldn't want to. So we'll just leave it like that, because it won't matter. It won't affect how we do this. So this is equal to, all right, now notice -1 to the n plus 1 and -1 to the n leaves us a -1 left over up here. So now I'm ready to write that, because that's the only thing that really went away. So that's the limit as n goes to infinity of -1 times n squared plus 1 divided by n plus 1 squared plus 1. And that's infinity over infinity, your friend and mine. So infinity over infinity, so therefore I'm going to use L'Hopital's rule. The -1 doesn't really matter that much because you could pull it out and make it positive since it's inside an absolute value. So it's kind of irrelevant. But what does matter is the derivative here. So if I took the derivative of this part, so you can kind of just ignore the -1. We don't need it. So it would just come out in front. If you want, you could put 1 right here. Here, I'll do it this way. There you go, 1. So that 1 is no longer in consideration. So now I just want to take the derivative of n squared plus 1. So that would be 2n over, oh, I didn't give myself enough space. Rats. 2n, and then it'd be 2 times n plus 1. Oh, I guess that's it. Because 2 times n plus 1, the derivative of the inside part is 1, and the derivative of 1 is 1, so I can write that bigger. Sorry. I was worried that I needed more space, but I'm all right. Well, that's still infinity over infinity, which we don't really have to do all these steps. We know what this is going to be based on the table we learned in 10.2 for a rational expression, which this is. These are both polynomials, so therefore I know it's going to be the lead of the coefficients, which is 1 and 1, but let me prove it to you, because 2 divided by 2, in fact, makes 1. So if I use L'Hopital's rule again, it would be the limit as n goes to infinity of 2 over 2, which is 1. Oh no, we're in trouble because that means that the ratio test was inconclusive. Boo. All right, well, I still need to test whether this series converges, and the ratio test did not work. So that means that I am stuck using other tests. So let me make a note. Have to use another test. Okay, well, looking up at it, I can tell that it's an alternating series. So I'm thinking, why don't we test for absolute convergence first? And if that doesn't work, then we can test for conditional convergence with the alternating series test. So let's try. Absolute convergence. Okay, let's try it. So if I want to test for absolute convergence, I would want to take the absolute value of b sub n and make that a series, which would be getting rid of that negative 1, getting rid of that negative 1 to the n part. So that would be 1 over n squared plus 1. And at this point, little bells should be going off in your head because that looks very similar to a series that we know about, a P series, right? So this is very, very, very similar to a P series that we know. All right, so we can use the series that we know, which is 1 over n squared. Now, this series is less than this series because it has a larger denominator. Remember that the larger denominator makes the overall fraction smaller. So this fraction is smaller than this fraction. All right, so that justifies this symbol being this way. So that's why the symbol is a less than symbol. All right, wonderful. Now, why is that useful to me? Well, this series is a convergent P series. The P value being 2, which is greater than 1. So I just did a comparison test. Right? This series is less than this series, and this series converges, therefore this one does too, by the comparison test. So therefore, comparison test. Right? I just did a quick comparison test because that was really close to that P series. And therefore, our series, which was b sub n, which is negative 1 to the n over n squared plus 1, converges. Because it converges absolutely. I guess I should say absolutely up here. Right? So we prove that the absolute convergence happens. Once the absolute convergence happens, that means that the series converges.